It really feels like everywhere you look these days, the modern world is just designed to fail spectacularly.
Right.
I mean, not just fail, but spectacularly fail. 1 minute, everything is humming along. You've got power, money in the bank, your supply chain is moving.
And the next.
And the next, half a continent is dark, or a major financial institution is suddenly just insolvent. It feels like we've engineered ourselves into these systems where these massive, almost cinematic failures seem, well, built in.
They do.
So why are these disasters so magnificent, and why do they feel so impossible to predict?
Well, that feeling of impossibility, that sense of the unpredictable black swan event arriving, randomly from the outside, that is precisely the fundamental problem.
Yeah.
We spend all our time treating these events as external shocks, but the author we're looking at today, Ted Lewis, he has this really radical question. What if the system itself, its design, its drive for efficiency, its very physical and mathematical structure, is the primary internal cause of its own catastrophe?
That's a huge shift in thinking.
Yeah.
The idea that failure is engineered, that's the core of what we're diving into today.
Exactly.
And if you are just joining us, welcome to the Strategy Sync YouTube channel. Please subscribe and like to hear new book summaries. Our focus today is a deep dive into the compelling work of Ted G. Lewis, specifically his book, The Science of Resilience.
Mm-hmm.
And this book is the culmination of more than 20 years of studying everything from nuclear power plant collapses to market crashes.
And Lewis's central thesis, it actually gives us some hope. Because if the system structure is partially responsible for the disaster, then we can analyze that cause and effect relationship.
We can measure it.
We can measure it, and more importantly, we can strategically improve that structure.
Mm-hmm.
And this moves us entirely past just reacting to risk and into proactively designing for quantified mathematical resilience.
And he's not talking about vague assurances, is he? He anchors his entire approach on quantification. It reminds me of that famous Lord Kelvin quote.
Oh, I know the one.
When you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind.
Exactly. That's the mission of the book, to find an objective way to quantify risk and resilience using actual measurements, using mathematics, so we can move beyond these, vague feelings of fragility or a subjective guess at recovery time.
We need a number.
We need a scientific, measurable number that acts like a structural stress index for any system, whether that's a forest or a stock exchange.
Okay, let's unpack this approach. Lewis starts by referencing Charles Perrow and his normal accident theory, or NAT. Perrow looked at extremely complex environments like chemical plants, NASA control centers, and drew some pretty grim conclusions, didn't he?
He really did. Perrow, he postulated that failures in these complex, tightly coupled systems are designed in.
Designed in.
Meaning they aren't random external shocks. They're inevitable outcomes of the system structure, and they're often compounded by management issues. Perrow believed that a minor or normal accident spreads and magnifies. He cited an invisible force that gradually builds up over time until the system just loses control.
And Lewis's goal?
Lewis's goal, across his decades of research, was to finally identify and quantify what that invisible force actually is.
So before we get to Lewis's solution, how does the engineering world traditionally calculate risk? What's the standard model?
The traditional way is a framework called probabilistic risk analysis, or PRA.
Yeah.
It's a really simple multiplication model.
Okay.
It calculates risk by multiplying three main factors: the likelihood of a threat, the likelihood of vulnerability to that threat, and the consequence.
So if I'm getting that right, you're just saying if the probability of the threat is low, the vulnerability is low, and the consequence is low, then the overall risk is low. Just simple multiplication.
Exactly. Risk equals T times V times C. And C, the consequence, is usually measured in things we can count: dollars lost, lives lost, or even time required for recovery. In this model, it works fine for simple, linear systems.
But you mentioned it utterly fails when we're dealing with truly complex systems. So why does that simple probability just break down when things get complicated?
Because complex systems, especially when they're stressed near their limits, they don't behave linearly at all. And they certainly don't obey the standard normal distribution.
The bell curve.
What everyone calls the bell curve, yeah. The bell curve assumes outcomes clustered neatly around an average. It means extreme events are supposed to be statistically improbable outliers. Way out there, several standard deviations from the mean.
But that's just not what we see in the real world. Not with financial markets or power grids or natural disasters.
Precisely. In complex systems, the failure distribution is inherently long-tailed. Just think about earthquakes or market fluctuations. Most events are tiny tremors or small dips, right?
Right.
Some are larger shakes or drops, and a rare few are truly astronomical catastrophes. That tail just stretches out, way out, meaning those extreme events are far more likely than the bell curve would ever predict.
So if you're relying on a normal distribution,
You are severely underestimating both the probability and the potential size of those rare, spectacular events. Lewis argues that this nonlinear behavior is the mathematical signature of a complex system that's heading towards spectacular failure.
so Lewis just rejects standard probability here. What does he propose instead? How does he capture this inherent potential for catastrophe? This is where it starts to get a bit technical.
It does, but the concept is really powerful. He advocates for using something called exceedance probability, or EP, and then modeling it using power laws.
Okay, hold on. Let me stop you there and just translate. Exceedance probability. That sounds like a fancy way of asking, what's the chance that the consequence will be bigger than X?
You absolutely nailed it. EP is simply the likelihood of an event whose consequence is at least as large as or larger than some size you designate. It forces you to look at the tail of the distribution first.
Got it. Okay, so why are power laws the right mathematical tool for that job instead of, traditional probability?
Because power laws accurately model that long-tailed exceedance distribution. And here's where Lewis makes his major leap.
Okay.
Instead of trying to measure infinite variables, he simplifies the entire analysis down to a single critical factor. This factor is the slope of the power law line, which he calls the fractal dimension. And it's represented by the letter Q.
Okay, so Q becomes the one number to rule them all, the system's stress index.
Precisely. Think of it this way. If a system's failure follows a long-tailed power law and its fractal dimension Q is less than 1, that's the critical threshold. The system is mathematically classified as complex, and it holds the potential for complex catastrophe. The smaller Q gets, the shallower the slope, which means the longer and fatter that tail is. That's quantifiable proof that the risk is increasing and the resilience is decreasing.
Wow.
Lewis makes this powerful case that this single factor, Q, quantifies the system's inherent structure and its tendency toward collapse. It's the metric for Perot's invisible force.
That is genuinely fascinating to really anchor this very abstract math in a concrete image. Lewis uses that foundational thought experiment sandpile metaphor
Ah, yes, the BTW experiment.
from the mid-1980s.
The BTW experiment, named for Bach, Tang, and Weisenfeld, is the perfect physical analogy for complex catastrophe. Imagine you're just pouring grains of sand one by one onto a flat surface.
Okay.
Initially, the pile just grows smoothly. The inputs are simple. The sand grains themselves and the stress they cause, the weight and collisions. The outputs are the growing sand pile and the occasional avalanche.
And what happens when the pile just naturally reaches a certain point?
It reaches an extreme inevitable state called self-organized criticality, or SOC. At this critical point, the slope is maximized, and adding just one more tiny normal grain of sand, a tiny input can trigger an avalanche.
It could be a small one.
It might be small, just a few grains rolling down, or it might be catastrophic, a massive cascade of grains.
Yeah.
But the crucial insight is that the size of these avalanches is not random. It's governed by a power law distribution. The catastrophic events are mathematically built into the structure of the system once it organizes itself into that critical state.
So the system, just by existing and operating normally, eventually builds up the internal structure that's required for its own downfall.
That's the scary part, isn't it? That's why Lewis links this to the idea of the 21st century being defined by punctuated reality.
Which means what, exactly?
Punctuated reality is the observation that modern-day events don't happen smoothly or randomly.
Yeah.
They come in bursts, clustered by time, space, and consequence. And those bursts, whether we're talking about massive wildfires, high-speed financial trading spikes, or even political protests, they all follow that predictable power law distribution. The sand pile is the fundamental model for any system that collapses under internal pressure once it reaches that critical self-organized state.
So now that we have the math, the power law, and this fractal dimension, let's explore the implications of those long-tail distributions, specifically the concept of scale.
Right.
Lewis argues something that feels, really counterintuitive at first, that big events are often just scaled-up versions of small events.
This is the concept of a fractal. And fractals are self-similar. They look the same regardless of the scale at which you observe them. If you zoom in on a coastline, you see small bays and inlets, zoom out, and you see the same pattern in larger bays and inlets. A long-tail distribution is inherently scalable or self-similar. The pattern of failure remains the same. The implication, when you apply it to risk, is profound. Major catastrophic earthquakes are mathematically just scaled-up versions of tiny, insignificant earth tremors. Large financial collapses are scaled-up versions of daily market dips.
That is a staggering way to look at history. It reminds me of that quote, the one often attributed to Mark Twain. History doesn't repeat itself, but it often rhymes.
Lewis looks at that through a fractal lens.
Right.
History doesn't repeat identical events, no, but it repeats a self-similar pattern at different scales. If you look at major political uprisings like the Arab Spring,
Right.
they follow the same bursty power law behavior patterns as smaller, more localized events like the Occupy Wall Street movement. They're all political protests operating at different magnitudes, but they're following the same underlying fractal structure.
This realization about structure and scale leads Lewis to emphasize three big recurring ideas in complex systems theory. They seem like the keys to the entire book, really.
Yes, absolutely. If you can remember these three concepts, you basically understand the architecture of systemic collapse.
Okay.
First, self-organization. This is the natural, inevitable process where the parts of the system arrange themselves, often toward that self-organized criticality, that SOC state, just like the sand grains arranging themselves until the pile becomes maximally steep.
Okay, one. What's two?
Two is phase transition. This is the critical tipping point. Once the system crosses this threshold, the point of no return, the consequence behavior radically changes. This is the moment a normal accident suddenly transforms into a catastrophe because the consequences start increasing exponentially.
And the third?
And third is structure. The connectivity and topology of the system, how everything is physically or financially linked, largely determines how the system responds to stress. In these systems, structure is destiny.
Let's apply this to a devastating real-world case study, California wildfires. Lewis uses decades of data on acres burned to illustrate the power of EP and this fractal dimension.
The data for California wildfires is chilling. It's direct, measurable evidence of this structural degradation over time. Wildfire consequences, the acres burned, they obey a long-tailed power law.
So you can track the Q value?
Exactly. By tracking the fractal dimension Q over time, we get a direct, objective measure of the changing risk. And look at the historical numbers Lewis presents. Between 1989 and 2005, Q was 0.91.
Which is very close to that critical collapse point of 1.0.
Very close. The system was stressed, but still, you could say it was relatively resilient.
But the situation has fundamentally deteriorated since then. It's moved us further into the red zone.
Dramatically so. From 2006 to 2023, Q dropped significantly to 0.77. And in the most recent, most intense stretch of fire seasons, from 2017 to 2023, Q declined even further to 0.55. And just remember our definition. When Q is less than 1.0, the risk is catastrophic. When Q decreases, getting closer to zero, it means the tail is getting drastically longer and fatter. This is mathematical proof that the risk of negafires is increasing and the system's resilience is decreasing. It validates that the catastrophe potential is worsening over time because of internal system changes, not just, bad weather.
And that brings us right back to structure and self-organization, specifically with something called the Yellowstone effect. How does the model developed by Turcotte and Malamud using percolation explain this worsening risk in terms of the forest fuel load?
Right, their model used percolation. Imagine randomly planting trees on a grid. Percolation is the process where objects, in this case trees and undergrowth, start filling up the empty spaces until they form these large connected clusters.
So density and connectivity increase dramatically.
Exactly, and they called the resulting self-organized criticality the Yellowstone effect.
And the counterintuitive lesson here, it directly relates to U.S. forest management policies, especially before the 1970s.
Absolutely. Prior to 1972, the policy in Yellowstone National Park was aggressive fire suppression. The goal was to put out every small fire immediately.
Which sounds like a good idea.
It sounds like a good idea, but it had a devastating unintended consequence. It caused a massive accumulation of dead trees and dense understory. It allowed the forest to become fully percolated, one giant connected fuel source.
So when a fire finally did ignite,
like the major fire in 1980, the result was a mega fire that destroyed 800,000 acres.
So preventing all those small, normal accidents actually guaranteed a complex, catastrophic phase transition later on.
Precisely. The key to resilience is reversing that percolation. It's structurally better to encourage smaller, controlled burns or to systematically thin forests. These are practices that actively reduce density and connectivity,
You're breaking up the fuel source.
and breaking up the large connected clusters of fuel, ensuring the system avoids that critical phase transition where consequences just spike exponentially. If the goal is to reduce megafires, it pays to actively depercolate the landscape.
Now, beyond just the acreage burned, the consequence, Lewis also stresses that resilience is a function of time. What are the key time metrics for understanding a system's resilience?
Right, risk is always a function of time. We want to maximize the time between incidents, that's the interarrival time, and we want to minimize the time it takes for the system to recover after an incident.
The recovery time.
The recovery time. And Lewis formalizes this using MPT, maximum probable time. This is the longest recovery time we should reasonably expect, and it's calculated based on the exponential exceedance probability function of recovery time.
And the ultimate goal is to minimize a combined metric, right?
Yes. The overall measure of resilience combines both consequence and time. You want to minimize the product of maximum probable loss and maximum probable time. That's MPL times MPT.
That seems like a powerful framework for making decisions.
It is, because you could spend huge sums of money reducing the recovery time lowering MPT by buying expensive backup systems. But Lewis argues it's often structurally smarter and cheaper to spend that money up front, preventing the catastrophe entirely lowering MPL by improving your Q value or depercolating the system.
Shifting from forests to human-engineered complexity. The structure of systems like nuclear plants means that one tiny failure can rapidly cascade into a global disaster. The 2011 Fukushima disaster provides a horrifying example of this multi-system fault propagation.
Fukushima it's the perfect illustration of how connectivity turns a local event into a global avalanche.
So the initiating fault was the earthquake.
Right, the Pacific earthquake. That triggered a secondary fault, the tsunami. The tsunami then overwhelmed the physical barrier, the seawall, which caused internal faults within the reactor systems, leading to the core meltdown. The disaster just propagated through geological, physical, and engineered barriers, spreading across global supply chains and economic systems.
That connectivity is the killer.
It turned a single initiating fault into a true catastrophe.
So how do engineers model these incredibly complex chain reactions or kill chains in systems like power plants?
They use something called fault trees. These are the basis of advanced probabilistic risk analysis, or PRA. They were developed extensively by Norman Rasmussen back in the 1970s.
Okay.
Fault trees organize potential failures as a hierarchical, logic-based graph. The nodes are faults or threats, and the branches are connected by Boolean logic gates. It essentially forces the analyst to map out every single possible failure pathway.
Let's talk about those logic gates because they seem critical for understanding why systems are built the way they are.
They're the architecture's DNA, really. The main ones are AND gates and OR gates.
Okay.
An AND gate means that two independent failures, say fault A and fault B, must both happen for the overall system consequence to occur. This is how engineers model redundancy.
Right, and an OR gate.
Conversely, an OR gate means that fault A or fault B or both will cause the consequence. OR gates are highly vulnerable because they reveal paths where multiple independent routes lead directly to failure. They effectively shorten the kill chain and increase the risk.
Now, Rasmussen originally predicted the likelihood of a major nuclear failure was incredibly small, basically ignorable. But his theories were tested and, well, arguably disproven by the 1979 Three Mile Island meltdown, TMI-2.
TMI-2 was the event that demonstrated that the sheer complexity and tight coupling of these systems just defies simple probability models. The failure chain was so long and relied on such a sequence of low probability events that it should have been statistically impossible.
But it happened.
But it happened. I mean, think of the chain. A leaking cup of water caused increased moisture, which tripped an air pressure signal, which stopped two pumps, which triggered the turbine wind down, which tripped the cooling water, which streamed into a blocked pipe, all culminating in operator error that led to the final meltdown.
That is a staggering sequence of dependent failures. It really felt like a true black swan.
It was a black swan because of the sheer length and implausibility of the sequence. But the system's design, its structure, allowed those low probability events to interact and multiply their consequences. And that ultimately resulted in the long-tailed exceedance distribution we keep coming back to.
So it proved that in complex systems.
It proved that the consequences increase more rapidly than the probability of those long chains decreases.
This brings us to a metaphor that's used constantly in risk management, the 100-year flood. We should probably clarify what that actually means in terms of annual exceedance probability, or AEP.
Yes, the 100-year flood is a classic example of misunderstood AEP. It means that in any given year, there is exactly a 1 in 100 or 1% chance that a flood of that magnitude or greater will occur.
But crucially, it does not mean it happens every 100 years and then you're safe for a century.
Exactly. And when you apply the math of repeated independent trials, the actual probability of catastrophe gets alarming.
How alarming?
If an event has a 1 in 100 chance of occurring annually, the probability of it happening at least once over a 100-year period is approximately 63.4%.
Wow, that's much higher than 1%.
Far higher. And if you live somewhere for 459 years, the probability of having experienced at least one 100-year flood rises to 99%. The core takeaway, which links right back to TMI2, is that a mega flood, or any catastrophe with a known AEP, should be expected within a foreseeable human timescale. It shouldn't be seen as a surprise event. The structural risk is built into the timeline.
Okay, so dealing with that risk costs money. Lewis introduces this crucial concept of buying down risk. How does he model investment in security and resilience remedies?
So when you invest money, say installing a stronger firewall or building a higher seawall, you're trying to reduce the vulnerability factor. V. Lewis models this vulnerability reduction using an exponential function that shows diminishing return.
Diminishing returns.
The key insight is that the first dollar you invest has a significantly greater impact on vulnerability reduction than the last dollar you invest.
So putting up the first strong barrier is paramount, but adding the 10th, slightly stronger barrier might give you only a negligible benefit.
Precisely. The vulnerability V decreases exponentially with investment. This helps analysts prioritize. But because fault propagation through a complex fault tree is nonlinear, you can't just identify the single most vulnerable component and throw your entire budget at it.
Why not?
Because fixing one part often just pushes the vulnerability somewhere else in the system. So this required Lewis to develop a smart optimization process.
So how do you find the optimal budget allocation when the system's reaction is nonlinear?
Lewis developed a heuristic, it's a kind of intelligent search method, to solve this. Since you can't use a simple formula, the heuristic uses a brute force trial and error method. You repeatedly exchange a small, fixed amount of investment money between randomly chosen threats or faults.
And you just see what happens.
You see what happens. If that tiny exchange reduces the overall tree risk, you keep the new allocation. If it increases the risk, you revert it. You just repeat this tens of thousands of times until the risk stabilizes. And that finds you the best allocation point where the overall tree risk is minimized for your limited budget. It's basically a guided guessing game to overcome the system's nonlinear behavior.
That model works for passive threats, like tree branches or normal system decay. But what happens when the threat is active, like a rational human attacker in, say, a cyber scenario?
That introduces a whole new level of complexity.
Wow.
Genuine competitive complexity. Now we enter the realm of Sackelberg competition. This is a two-player, non-cooperative game.
Okay.
The attacker acts rationally to maximize the threat, TX, using their resources, while the defender simultaneously tries to minimize the vulnerability, VX, using theirs. The resulting solution seeks a minimax equilibrium, where neither party can unilaterally improve their strategy because the other party is always anticipating and reacting.
So your investment priorities have to change.
Drastically. It's a completely different allocation compared to a passive defense model.
Now, if we identify a major fault, one common defensive strategy is just adding redundancy, like having a spare cooling pipe in a nuclear plant. How does Lewis model the effectiveness of that?
Redundancy is modeled explicitly using an A and D gate. The original pipe and the spare pipe must both fail for the fault to propagate up the tree. In the TMI2 model, investing in that redundancy shifted the consequence of a single pipe failure to zero, as long as the redundant pipe didn't also fail.
So it's a powerful tool.
It's a powerful tool, but it too suffers from diminishing returns. At some point, the cost of adding a third or fourth redundant layer just outweighs the marginal benefit of that extremely slight reduction in risk.
Everything we've discussed so far, fault trees, fractal dimension, it all comes back to this idea that structure is destiny. So now we move fully into network science, where connectivity is the ultimate source of complexity and fragility. What quantifiable metrics does Lewis use to characterize the physical shape and stress points of a large network, like a power grid?
We use several metrics. There's density, which measures how tightly connected the system is. Diameter is the measure of separation, the shortest path between any two nodes.
Okay.
But for anticipating catastrophic collapse, the two most important metrics are between latitudinous centrality, which helps you spot the bottlenecks, and the spectral radius.
The spectral radius, that sounds highly technical. How
Yeah.
can we explain that simply?
The spectral radius is the largest eigenvalue of the network, and it is overwhelmingly correlated with the influence of the most central hub node in that network.
So it's like a centralization score.
That's a great way to put it, a network centralization score. And fault propagation, that cascading failure, it increases dramatically in frequency and intensity the higher that spectral radius is. A high spectral radius means one node failure can quickly take down the entire system.
And we saw the horrifying result of high connectivity in that massive 2003 Northeast blackout, which affected, 50 million people across the US and Canada? Let's revisit that catastrophe.
That blackout is the textbook example of a catastrophic cascade triggered by an initial minor fault in a highly coupled network. It began at 2:02 p.m. EDT in Ohio when a 345 kV line tripped because it simply contacted a tree.
A classic, small, normal accident.
Exactly. That was phase one, power degradation.
But the immediate fault wasn't the disaster. It was the operator's subsequent blindness.
That's phase two, computer failure. The first Synergy SCADA's alarm software failed almost immediately. And SCADA systems are the eyes and ears of the grid operators. When the primary alarm failed and then the backup failed later, operators were essentially flying blind.
They had no idea what was happening.
They couldn't diagnose the problem, couldn't see which lines were overheating due to rerouted load, or understand the scale of the growing crisis. They knew something was wrong, but they had no precise structural information.
And that information blackout allowed the uncontrolled cascade phase third to just run wild, demonstrating the true vulnerability of the network structure.
Exactly. By 3:05 p.m., the Harding-Chamberlain line overheated and shorted with another tree. And because operators couldn't respond strategically, the uncontrolled cascade began. A failure in Ohio tripped lines that affected non-adjacent parts of the system, like New York and Michigan, all due to rerouted flows and the overloading of alternate paths. This tight, complex connectivity allowed a small fault to become a multi-state collapse.
In networks that deal with flow-like power grids, pipelines, or physical supply chains, what structural features are the key determinants of resilience?
Flow network resilience depends on two structural features. First, the presence of numerous alternate paths from the source nodes to the sink nodes. More alternate paths mean more resilience because you can reroute flow.
Makes sense. And second,
The absence of bottlenecks. Bottlenecks are usually nodes that have high playum between alignment and centrality. They lie on the most shortest paths. If you remove these blocking nodes or links, they segment the network into isolated, non-functional islands.
Lewis introduces a brilliant way to characterize network structure using the ratio of these metrics, bushy versus branchy networks.
Right. Bushy networks are characterized by a high spectral radius, high centrality, and a low diameter, short path lengths. Think of centralized organizational charts, highly efficient, scale-free networks like the 9/11 terror cell structure or the Texas ERCOT power grid.
They're efficient, but
They're efficient for flow, but since they rely on massive central hubs, they are extremely susceptible to targeted attacks and cascading failure. They're brittle.
and the alternative, the branchy network.
Branchy networks have a low spectral radius and a high diameter. These are distributed systems, like the LA Metro system or a series of ferries running distributed routes. The central finding in the analysis is that the maximum probable loss, the MPL from an avalanche, is overwhelmingly correlated with bushiness. Bushy networks are structurally less resilient to cascading failure.
Because hitting the central hub.
Hitting the central hub, the node associated with that high spectral radius, causes the greatest possible damage.
What about systems that don't deal with simple flow from A to B, but rather require every part to be in sync, like the internet or the highway system?
Those networks often contain feedback loops, or cycles, which introduce the risk of severe instability. A power grid, for instance, has to maintain synchronization. If a line trips, the electrical circuit can be sent into exponential oscillations, which leads to a system-wide collapse because it loses the rhythm.
So the key resilience factor there is self-stabilization.
Exactly. Self-stabilization.
And how do we guarantee a complex system achieves that rather than falling into continuous oscillation?
Stability is achieved in what are called aperiodic networks. Now, this is technical, but think of it with a clock analogy. If all the intersecting cycles, the energy loops within the network, have time lengths that are relatively prime, meaning they don't perfectly align and repeat simultaneously.
They don't sync up.
Then the network is mathematically guaranteed to self-synchronize and stabilize, eventually reaching a fixed, steady state. Periodic networks, where the cycles perfectly align and oscillate, are inherently unstable and prone to failure following a disturbance. This aperiodic structure is essential for any functional cooperative system, whether it's a biological nervous system or a power grid.
This analysis leads us to the fundamental question that really underlies Lewis's entire work. If structure dictates destiny, and we know centralization and tight coupling increase fragility, why do we keep building these fragile, optimized systems?
This is the core tragedy, isn't it? The optimization paradox. Our natural human inclination, driven by cost reduction, profit maximization, political pressure to deliver services cheaply, is to optimize systems for maximum efficiency.
Right.
But Lewis, building on Purbach's self-organized criticality, states it clearly. Optimization inherently increases SOC and simultaneously decreases resilience. We're actively engineering fragility into our lives.
The ultimate, unforgettable, real-world example of this paradox for the modern listener has to be the supply chain crisis of 2020.
Absolutely. The highly efficient, just-in-time supply chains were optimized for profit, delivering goods with minimal inventory and eliminating costly redundancy. They were the absolute epitome of efficiency.
Until they weren't.
When the unexpected stress of the COVID-19 pandemic arrived, they failed robustly because they lacked the necessary redundancy and excess capacity. They had no structural flexibility. They just couldn't absorb the shock.
And the government response made it worse?
Well, when the government tried to overcompensate, say by producing ventilators, the system violently swung to the opposite extreme, resulting in a glut after the initial shortage. This just demonstrates the fragility that was optimized right into the system.
And speaking of counterintuitive results in flow networks, what is the Brace paradox? It seems to directly defy the logic of optimization.
It does. The Brace paradox states that adding capacity to a flow network, say, building a new, highly efficient lane on a congested highway, or adding a new fiber optic trunk line, may actually reduce total flow or decrease overall resilience.
How is that possible?
It happens because people act rationally to take the new efficient route, but this floods new bottlenecks that didn't exist before, resulting in overall worse system performance than before the improvement. It just shows that topology and structure have nonlinear effects that defy simple optimizing logic.
So optimization isn't just about reducing resilience. The process of optimizing systems actively increases fragility in several specific emergent ways.
And that process is often driven by preferential attachment, which is essentially a natural positive feedback loop. It means that networks naturally evolve toward favoring nodes that already have a slight advantage.
The rich get richer effect.
Exactly. The network equivalent of the rich get richer.
And this creates three specific types of fragility. Let's start with centralization, or what Lewis calls degree emergence.
Degree emergence is what transforms a random network into a scale-free network. Through preferential attachment, a few nodes gain a huge number of links. They become the high-degree hubs, while most nodes remain peripheral.
And this jacks up the spectral radius.
It dramatically increases the spectral radius. For instance, simulations show the spectral radius of a network can double after only a few thousand trials of preferential attachment. These hubs become centralized, attractive targets, and single points of catastrophic failure.
The second emergence relates to eliminating redundancy, which just sounds like basic corporate cost-cutting.
And it is. That's link emergence. It's driven entirely by the goal of cutting costs. System designers remove what they see as non-blocking or redundant links. This results in sparse, branchy networks.
And there's a trade-off there.
A complex trade-off. Eliminating these redundant links can actually improve avalanche resilience, a lower MPL, because the pathways for a massive cascade are reduced. However, it severely reduces flow resilience, measured by bottleneck Z, because there are fewer alternate paths. You save money, but if one link breaks, the traffic jam is instant and catastrophic.
And the third way fragility emerges is through the modern tendency towards standardization and automation.
We call this monoculture, centralization and automation. Modern systems like financial data centers, so-called telecom hotels, or the global internet's top-tier carriers, they are standardized, which makes mass attacks easy. They are centralized, so the hubs become attractive targets. And they're highly automated, which allows faults or malware to spread rapidly across the highly coupled system before human intervention is even possible.
So it's the perfect recipe for maximizing catastrophic risk.
It's the trifecta.
So if structure is the problem, the solution has to be restructuring. How does Lewis propose we proactively defeat this tendency toward catastrophic phase shift?
By strategically reducing the spectral radius, which means reducing the size and influence of those massive vulnerable hubs. Lewis introduces the node-splitting heuristic.
Okay.
This strategy involves identifying the node with the largest number of connections, the hub, and splitting it into two smaller, approximately equal nodes, then reassigning roughly half the lengths to the new spare node.
That sounds like a brilliant surgical solution. You're increasing resilience with a minimal increase in resources.
Exactly. You are structurally depercolating the network. Lewis applied this to a simulation of the Texas ERCOT power grid, which we know is a notoriously bushy network with a high spectral radius.
Right.
By applying the node-splitting heuristic to just 5 critical nodes, the maximum degree of the largest hub dropped dramatically, from 313 connections down to just 78.
And what was the quantifiable impact on resilience? What did the numbers say?
The simulation showed a massive 61.6% improvement in the maximum probable loss, the MPL, the N1Z resilience, the network's ability to handle the removal of any single node without cascading failure improved by 6.2%.
But there was a downside.
A very slight one. There was a small decline in flow resilience, about 2.3%, because splitting nodes sometimes reduces alternate paths. It just illustrates that structural trade-offs are inherent. But the overwhelming benefit was the quantifiable reduction in catastrophic risk.
Let's talk about how these same principles, scale-free networks, centralization, phase transition, how they govern biological and socioeconomic systems. Lewis returns to Gauss's competitive exclusion principle. Small advantages leading to system dominance.
Right. Gauss's principle is the engine behind preferential attachment and centralization. In biology, one species with a small reproductive advantage will eventually drive another to extinction. In economics, this is the network effect. Small advantages led to dominance for platforms like Microsoft or Meta.
And this mechanism, it naturally creates these high-degree hubs.
It does. And they increase efficiency, but simultaneously lower system resilience by centralizing power and control.
We saw the application of these models to physical wildfires. How about biological contagions like the rapid spread of the COVID-19 pandemic?
The spread of an epidemic is an exact analogy for a biological avalanche. High connectivity like international travel hubs, say LAX, and high population density enable a rapid phase transition, allowing the virus to spread like wildfire across the globe.
And the resulting contagion network isn't random.
Not at all. It quickly becomes scale-free, defined by its long-tail distribution of consequences.
And the hub of that contagion network is what we all came to call the super spreader.
Correct. The super spreader, an individual or a specific location, is the high-degree hub responsible for the vast majority of infections. This scale-free structure is what makes pandemics particularly challenging.
But the models offer a solution.
They do. Lewis's models show that even a small amount of herd immunity, say 5% to 20%, drastically increases the critical point for phase change and significantly reduces the overall consequences. In essence, immunity acts as a form of depercolation, structurally breaking up the connection clusters.
Okay, now let's turn to the ultimate structural failure in socioeconomics. The tragedy of the commons, or TOC.
William Forster Lloyd's original parable, which was made famous by Garrett Hardin, illustrates a critical structural failure mode.
Which is?
Rational, self-interested action leads inevitably to the depletion of a shared, finite resource, the commons. Individuals maximizing their own gain push the system past its carrying capacity, resulting in self-destruction or extinction of that shared resource.
What are the modern, everyday examples of this TOC that Lewis highlights?
They range from environmental issues like air and water pollution to systemic financial risk. Lewis highlights the concept of too big to fail banking.
Right.
Where institutions privatize profits in the good times, but effectively shift their catastrophic losses onto the taxpayer, the commons, when they fail. But perhaps the starkest infrastructure example is the U.S. interstate highway system.
How so?
It's a shared commons whose fixed funding mechanism, the Highway Trust Fund, is stuck. Money is spent just maintaining the overgrazed, the overused and decaying system instead of extending or modernizing it. And that leads to the inevitable decline and eventual structural extinction of the asset if it's left unaddressed.
Now, Lewis dedicates significant space to applying these complex models to the 2008 financial crisis, viewing it through the lens of TOC and the predator-prey model.
This is a really powerful analogy. The financial system was pushed past its carrying capacity, K, by what Lewis calls enrichment. The prey was the stable housing market, and the predator was the financial system's exuberance and debt.
And this enrichment.
This enrichment involved lax lending standards, the proliferation of high-risk subprime mortgages, securitization, which hid the risk, and government housing policies that were aimed at unsustainable homeownership rates. This over-enrichment pushed the system to its critical point.
The resulting structural failure was the extinction event in the financial sector, famously called a Minsky moment.
That's the point where over-indebted investors are forced to sell assets, causing prices to collapse and liquidity to just dry up. The system withholds assets, effectively reducing the carrying capacity, K, and leading to the global collapse that propagated across highly coupled financial markets worldwide. The classic predator-prey cycle of enrichment, oscillation, and potential extinction collapse to zero, it accurately models this financial pathology.
One of the most fascinating results in the book, and one that gives us some hope for proactive management, is the ability to use the predator-prey math to predict these financial collapses, the precursor signal.
This is truly valuable. By analyzing the time series data of market indices like the SPX 500, we can derive a precursor signal. It acts like a structural fever gauge for the market.
And when it spikes?
When this signal spikes, it flags an instability in the system's carrying capacity days or even months before a major crash. This method successfully flagged instability days before Black Monday in 1987, multiple times before the dot-com bubble burst in 2000, and critically, several times months before the housing market collapsed in 2008. It proves that the system gives structural warnings before its catastrophic phase transition.
Finally, let's look at social avalanches in the digital commons. Things like flash mobs and organized disinformation networks. The internet is the ultimate scale-free network.
It is, and modern flash mobs and conspiracy networks leverage the speed and connectivity of the internet, social media, viral messaging to spread ideas or memes. They're social contagions.
So how is resilience defined here?
Resilience here is defined differently. It's the maximum probable time, MPT. The network remains stable on one idea before a crossover to an opposing idea occurs. These time intervals between successive bursts of synchronization, they follow a power law distribution, indicating they're governed by SOC.
So if these conspiracy networks rapidly sync on an idea, how can Lewis's models be used to counter or block that synchronization?
Lewis proposes a countermeasure using control theory, and it leverages the network's topology. The goal is to prevent the network from synchronizing to complete consensus. And you do this by strategically pinning contrarian actors or injecting counterinformation at specific high-influence nodes.
You target the hubs.
You target the nodes with the largest eigenvalues, the high-degree hubs, because they have the greatest structural influence on the network's overall behavior.
And the research shows this is highly effective, even with just a small number of pinned contrarians.
Remarkably effective. For a complex social network simulation, it was the Facebook 4039 network, where the most influential node was pinned to start a conspiracy. Only 1.1% of randomly chosen contrarians were needed to prevent the conspiracy from fully synchronizing across the network.
That's incredible.
It demonstrates that topology dictates control. Targeting the highest influence structural points is an efficient strategy against large-scale organized disinformation.
Okay, let's unpack all this. We started with the simple feeling that modern systems are fragile, and Lewis argues he has quantified exactly why and, well, given us the tools to fix it. So what does this all mean for you, the learner? What are the core lessons from the science of resilience?
I think the first core paradox is that the relentless pursuit of efficiency and optimization inherently reduces resilience. It drastically increases vulnerability to catastrophic long-tailed collapse.
Right.
By removing redundancy, eliminating slack, and centralizing assets to cut costs, we push systems closer to the inevitable, predictable structural failure of self-organized criticality.
And the second key lesson is that structure is destiny. External threats are only half the story. The internal structure, the connectivity, the centralization score or spectral radius, and that structural stress index is often far more predictive of spectacular failure. Bushy, highly connected, scale-free systems are brittle and prone to cascades, whereas branchy distributed systems are inherently more robust against collapse.
And finally, the power of Lewis's approach is to transition from vague feelings of fragility to quantified risk. By moving the metrics to exceedance probability, EP, in the fractal dimension Q, we gain proactive control. We can use methods like the diminishing returns model for strategic investment, or surgically restructure systems via node splitting to reduce spectral radius, effectively buying down the catastrophic potential before the disaster even begins.
The entire journey through this book shows that our most efficient human-engineered machines are structurally the most fragile. They're setting us up for predictable, massive failure.
Indeed. The author's conclusion is stark. He says, the most efficient machine may be harmful to human operators and lead to an eventual catastrophic end.
Which leaves us with this final provocative thought for you to mull over. Lewis shows a state space diagram for the massive U.S. power grid from 2011 to 2023, and it is measurably trending towards an unsustainable zero fixed point, a trajectory that has been continuing since the 1960s. We know from the wildfire case study that local structural solutions involve deep percolation. So what proactive system-wide restructuring strategy, beyond the local node-splitting solutions we discussed, should policymakers prioritize today to fundamentally reduce the spectral radius of the entire U.S. power grid and prevent its predictable, inevitable collapse? We'll see you next time for the next deep dive.